So we talked about electron configuration, and we talked about how it's associated with the shape of the periodic table. But there's actually more evidence for these energy levels and the order in which they go. And it comes from a field of study called photoelectron spectroscopy. And so our current learning goal is that you would be able to connect the idea of the photoelectron spectrum with the electron configuration, and also associate that with the interactions between the electrons and the nucleus, the attraction. So let's talk about photoelectron spectroscopy. Remember that when we shine light or somehow excite electrons, that they can emit photons, and those photons have different colors and things like that associated with them. Well, if you hit a element or some sort of substance with really intense radiation, you actually can emit an entire electron from that substance. And the electron, when it travels through space, this detector can analyze the energy of the electron that's been emitted from the surface. And then we can do a little bit of mathematical calculation to then determine the energy between the energy of the light, or a lot of times some sort of photon source, right? Some sort of light, X-ray, radio, something, hits the surface. And when an electron is emitted, the difference between the energy that hit and the energy of the electron that's emitted can be calculated as the binding energy for that electron. So what was the energy that had to be overcome in order for that electron to be emitted? And they can be read in a detector and interpreted in some sort of graph or spectrum. Okay. Now, the one that you see on the screen is like a rough spectrum, raw data type idea. The ones that you're going to see on the AP exam are simplified. So let's look at a simplified photoelectron spectrum. So what you're going to see is on the y-axis, you have the relative number of electrons. So the height of the peak and the area underneath the peak has to do with how many electrons have that energy. And on the x-axis, you see the binding energy. Now I want you to notice there's a unique thing about these, that they start at high numbers and get lower. Normally, when we do a graph, we start at 0 and we count up as we go to the right. In this case, the binding energy is the opposite. So we start at high energy and it goes down as we go to the right. And the reason that they do that is so that we can put these in order where we have the highest binding energy first is going to be the orbital that is the closest to the nucleus, because the nucleus is attractive to the electrons. And so it takes the most energy to remove the electrons that are closest to the nucleus. So now by switching around that binding energy and putting the high binding energy first, what we can do is ensure that the orbital that's closest to the nucleus is the first one that we see. And this puts the orbitals exactly in the electron configuration order. So in this example, you can see the first peak is low. That's the 1s. It has high binding energy. The second peak is lower energy or binding energy, right? And so this would be the 2s. And then the higher peak has more electrons. That's the 2p. And then you see another gap and there's a low peak. And in this case, only a slightly higher peak. Well, that's because in the 3p orbital, it's not quite filled. It might only be a 3p4. Maybe it's about twice as high as the s orbital. So this is more likely how you're going to see the PES, the photoelectron spectra, on an AP exam. So the peaks are associated with the electron configuration. The energy is associated with how close they are to the nucleus. This is binding energy. It's not the energy of the orbital, it's the energy of the binding. So how hard was it to remove an electron from that orbital using the laser or the X-ray beam that was exciting the electrons in the machine. Okay, so let's look at a couple of examples. I know this is new this year, that we haven't seen these spectrum before, but by using this relative number of electrons information, knowing how many electrons are in each orbital, and knowing the order of the orbitals for electron configuration, they should be relatively straightforward to figure out. So let's try a few examples. All right, so this example actually has lines, so you can see the relative intensity or the relative number of electrons, and it's asking you to match this spectrum with the electron configuration. So why don't you pause the video and give this one a shot. Okay, so we start at the highest binding energy, which is going to be the orbital that's closest to the nucleus. We call this 1s. And there are 2 electrons, so that all of these have 1s2. Then we go to the next grouping. We have a 2s and a 2p. And those are both full. We know that because we can count 2 and 6. Then we go to the third grouping, and we say the first thing that comes is S, and this 3s2. And then we have a 3p, and it's only filled to the third line. And this corresponds with choice B on the multiple choice here. So B is the correct answer. Okay, so the next question actually is asking us to compare the same orbital from 2 different elements. So pause the video, see if you can figure out what this is getting at, and then unpause the video and see how you did. Okay, so in this case, what we see is that the oxygen 1s orbital has higher binding energy. It's more attracted to the nucleus than the nitrogen. Why would that be true? Why would oxygen be more attracted to the nucleus rather than the nitrogen? Well, if you look at how many protons are in the nucleus and you remember those trends as you go across the periodic table, there are more protons in the nucleus. Those are more attractive, especially to the electrons that are the closest to the nucleus. And so the answer here has choice D, that nitrogens have a smaller nuclear charge than oxygen atoms. And because they have a smaller nuclear charge, the 1s is less attracted, meaning that the binding energy is lower. All right, we can eliminate this business about shielding or the repulsions or the subshells, because that all doesn't have to do with the binding energy. Binding energy has to do with the attractiveness to the nucleus. Okay, this next one is an open-ended question, and so there are a couple of things that it's asking you to do. The first one is to write the electron configuration, identify the element, and then calculate the wavelength in meters of the electromagnetic radiation needed to remove an electron from the valence shell. Notice that in this case, the binding energy is given in joules. It's very specific. And so to do this, we have to actually use some information from that AP cheat sheet, right, with all the equations and things on it. And you'll notice that the first section there is atomic structure, and it gives us some equations here. This is really just a plug and chug type idea. It tells us what the different symbols mean, frequency and wavelength, and it gives you a bunch of constant information there too. So I want you to see if you can work this one out. So pause the video, take your time, see if you can figure this out, and then I'll show you how to do it. Okay, so first thing we need to do is be able to write the electron configuration. So we start with the peak all the way to the left, and it's 1s, and then it's full, so this would be 2. And then we go to the next 2 peaks. We've got 2s2, 2p6, they're full. We go to the third grouping, 3s2, 3p6, it's full. And then we go to the last one. This would be 4s, and it's the same height as all of the other s's, and so this would be 4s2. All right, so that's your electron configuration. To identify the element, we need to go to our periodic table, and we go to the 4th row. S2 gives us calcium. So this is calcium is our element. And the last thing that we need to do is to calculate the wavelength. So if you look at your cheat sheet here, that's that like kind of upside down Y with a lambda. And so that is our symbol for wavelength. That's what we need to calculate from these equations. And what we're given is energy in joules. And so the energy equation we have is E equals H, which is Planck's constant, it's a number, times V, which is a frequency. But we don't have the frequency, and we're not being asked about the frequency. And how are we going to be able to? Well, we could calculate the frequency using the first equation. We know the energy, so we plug that in, 647 times 10 to the negative 18 equals Planck's constant, 6.626 times 10 to the negative 34 times V. We solve for V. Then we can use the second equation, which has this C equals wavelength times frequency, and C is the speed of light, which is another constant. So we plug in the constant for C, we plug in the value that we got for V, and we solve for the wavelength. And so this is a pretty simple calculator problem using the equations that are already provided for you. So this is a good thing to get comfortable with, to understand how energy is associated with light, the speed of light, the frequency, wavelength, remembering that frequency and wavelength are also related to each other. Inverse relationship, right? Because when you multiply them by each other, you get a constant. So as wavelength goes up, frequency goes down. As frequency goes up, wavelength goes down. But in terms of the actual calculations, these are really just plug and chug problems. So that is it for PES spectroscopy. It's brand new this year, but like I said, I'm pretty confident that you'll be able to get it with some practice. And that's the end of this video.